Hello folks, this is Tom from anti-proton.com, and today we're going to test something interesting. We're going to test Cesium-137. See? Cesium-137. And we're not going to use our super duper expensive equipment today. We're going to use equipment that's more accessible to most people. As you all know, I adore my UCS-30, but that's more of a lab grade piece of equipment. Let's use something that the common hobbyist can actually use. Something that's reasonably inexpensive, yet does a really good job, I think. And that's the Gamma Spectacular from B Research. I happen to have a GS111A right here. I think this guy is absolutely wonderful, and I take it with me a lot of times on trips because my UCS-30, as good as it is not really very portable for taking in trips. I use that at home in the lab. This guy right here is very field portable. I have a Ludlum sodium iodide detector. This is a 1-inch probe. This is a 44-2. Notice the Ludlum's got a little, the sticker's all messed up right here, but the metal's got a few dings on it, over time. I think the Ludlum just gets better as it gets older. Those little scratches and stuff it gets, it gives it this cool rustic feel to it, I don't know, I just kind of get into it like that. I have a laptop right here I picked up from Dell. When I got my really nice laptop, I got this little guy as an extra toy for it was I don't know, $200 or something, and it's been useful. It can't do anything the nice laptop can do, like games, but I can leave it on all the time without any worry about it. Very useful. I have a couple Cesium-137 samples right here. That's the source for another experiment I'm going to show you in a minute. That's a Cesium-137 sample I got from Spectrum Techniques. This guy was about $50, plus or minus. I can't remember the exact price, but about $50. I have another one right here. This is Cesium-137 in water. Very interesting sample in water. But anyway, yes, I've swipe tested it 1,000 million times. It's not radioactive by any means. But anyway, both of these are significantly hot. About 100,000 counts per minute. And a microsieverts per hour. And I'd like to point out that this is the only time that it's acceptable to use it for this, because see, this unit actually is calibrated to Cesium-137 gamma only, so there's actually nothing wrong with using it. I have the this turned upside down, see what I mean, to block the beta. And just to get an idea in milliroentgen per hour. 1.2. Yeah, that's about right. 1.2. That's about right, because it's about 12 microsieverts per hour. So that's right. All right, so we'll put that down. See, there is a time when you can use that. Now, we have a single power and data cable coming out. Some units have two. Like my lab grade stuff has two cables, a signal cable and a power cable that are this guy has them both combined. And they go into the Gamma Spectacular, into its input BNC jack. The output sound comes out to here, and the USB cable to the laptop provides power. And basically what happens is this. Positive voltage comes into this. It goes to this, and basically whenever a gamma ray hits the crystal, it produces a small flash of light, right? That flash of light, I think it's in the ultraviolet range, it hits the photocathode, which produces a burst of electrons, and the number of electrons it produces is proportionate to the intensity of the light, the number of photons produced. So gamma ray hits, produces photons, hits material that produces electrons. They get pulled down this tube here, a photomultiplier tube, and they get accelerated by the photomultiplier tube, producing a voltage, a current, which is proportionate to the number of electrons, which is proportionate to the number of photons, which is proportionate to the energy of the gamma. It all stays proportional. It's kind of interesting. So anyway, that goes down here and gets measured by this device, and you produce an X by Y graph of low to high energy and so on. I should point out the software that I use right here. This software, I love this software. I absolutely adore it. This is for, I'm showing it to you. I think this counts as fair use because I'm not actually showing you all of it. I'm just showing you like what I'm currently using. You can select all the isotopes that ever existed and look up all their information. and it's called iChart nuclides, and I'll put a link to that in there too. I use it for everything. Alright, so cesium-137 has a pretty simple decay scheme. We're going to take this, by the way, we're going to put it on a sample container, like that, stick it in our graduated sample container. This comes with a UCS30, I just happen to be using it. This is rolls of lead, aluminum wrapped, and nestled around the detector itself. The reason is that that blocks out some of the background for a cleaner spectrum. And then this is a sheet of aluminum that I use to try to cut down those beta particles, because beta particles that hit, I put that over top of the sample, in between the sample and here, beta particles that hit the detector here will create various types of additional interference, such as X-ray fluorescence. So now that I have that in place, you notice the spectrum's already responding to it, and we're going to calibrate this thing and get it all going in a minute and start it over in just a minute. And and we're going to see what it looks like. So we have everything hooked up. Now let's quickly talk about what cesium-137 does. Cesium-137 emits via beta decay. What that means is beta minus. What that means is that one of its neutrons is going to actually decay into a less massive particle called a proton. And in doing so, that extra mass has to go someplace, and it's going to go someplace in the form of a beta particle, which is, in this case, a beta minus particle is basically an electron. There's also going to be an electron antineutrino, and the two go flying off together as a pair. And that's why cesium-137 is a pretty potent beta emitter. The result is it will occasionally decay from cesium-137 via beta directly to something called barium-137. Directly to barium-137. Barium-137 is not radioactive by itself. However, most of the time, 80+% of the time, and in fact statistically it works out to 85.1% over time, you end up with something called barium-137M. Most of the decays go to that. What is that? Barium-137M is an unstable version of barium-137, which is normally not radioactive, but the unstable version has a huge amount of surplus energy because the nucleus is still really excited from the change. It hasn't calmed down perfectly yet. It hasn't gone right into place. It's close, but not perfect. Think of a basketball. Sometimes it goes right through the hoop. That's when it decays directly to barium-137. But most of the time, the basketball hits the hoop and bounces around and rolls or bounces and then eventually goes in. That would be barium-137M, metastable. Metastable meaning as it bounces around the hoop. It's not really stable, but it's not really unstable. It's kind of doing something and then it falls through. That's how the analogy works. And when that jump from barium-137M jumps down to barium-137, that difference, that surplus energy shoots off as a gamma ray at 661.66 kiloelectron volts. That's that right there. And there's a bunch of little X-rays that are emitted too. K-alpha-1 and K-alpha-2 X-rays. They go flying all over the place, and you see those down there. So anyway, let's calibrate the unit, get it all set up, and take a look at cesium-137. Cesium-137. All right, so now we're ready to take a spectrum. Most of these videos I've started by taking a cesium-137 spectrum and using that to calibrate my machine. Not because it's the best way to do it, but because it's the easiest way to do it if you're starting out, and the whole point of this is to show people starting out. But we're at a bit of a conundrum here because we're actually looking at cesium-137. So I'm just going to go ahead and take the spectrum, and then I'll show you the aspects of it. So here we are in PRA, and I have the height threshold in arbitrary units set to 0.7. Typically, I try to keep this pretty close to the resolution of the detector. But anyway, 0.5, 0.6, 0.7, 0.8, and 0.9 seem to be pretty good for most detectors, and you might want to play around with these settings to get it right for your detector. But basically, I'm telling the unit the highest peak I want to look for, and the peaks come from the sound. Let me show you. Let me minimize this quickly and start up Intune. Intune is a little piece of software which captures sound pulses from the detector. See, these are sound pulses coming from the cesium being recorded. See, the height of these sound waves is proportionate to the energy of the photon that hit the detector. So when I run a few of these and stop this and go back and look, I can see what it looks like. I think that could have expanded a little better now. But anyway, if I move my mouse along here, I can find that the highest peak right here is nearly 100, isn't it? No, it's much less than that. 30, 40. I'm looking right here at the maximum at arbitrary units. And I think this is reasonably good. Let me try to move this so you can see it. See? There's a positive and a negative part of it. So basically I'm trying to get the average of these to be somewhere in the 50 range. I don't know that I quite have that right, but it's not too far off. See, this peak right here is pretty average, and it's in the 40 range. So anyway, these sound pulses coming back are proportionate to the energy of the photon that hit them, because that's what the photomultiplier tube does. And so they'll be presented out here based on their energy. And this just tells me how high I want to reach. I don't want to go over 7. 0.7 in arbitrary units. That would be 70 on that chart back there, I believe, if I have that right. I get this wrong sometimes, but that's okay. Let's see here, the shape tolerance method. The lower this number goes, the more the less tolerant the software will be to accepting a peak. One of those peaks that comes in, if it's not very well formed, and this number is very high, it will still accept it, but if this number is very low, it will not. So this is how fine we want to be of our tolerance for the pulses not being shaped correctly. So the first thing we're going to do is we're going to go to Action, and we're going to go to Start Pulse Shape Acquisition. Now this may look like a spectrum forming, and sort of in a way it is, but it's not really, so just kind of, don't worry about it. I'm going to collect a few thousand pulses, and what the computer is doing is it's figuring out approximately what is a peak versus what is not a peak. And as a result of this, it's then going to come up with a set of numbers for what a perfect peak signal should look like. One of those little spikes we saw, a really, really good one. It's looking for what a really good one looks like. And then once it knows what a really good one looks like, then this right here, the shape tolerance, will be queued up to that. So the lower the number, the closer it has to match. Okay, I think I've gone on about that enough. We're going to pick about 10,000 pulses, so we're almost there. And then we're going to take a spectrum and give it about 20 minutes time-lapsed, of course. So stop. Here are all the data points for the shape of the peak. Just go and accept those. If you're a pure mathematician, you can go in there and play with them, but I'm not, so I'm not going to play with them. And then we're going to start. Now, we give this about 20 minutes to rise up to what it's supposed to look like. Time lapse, so give it less than a minute for the video to get up to that point. And then we're going to go calibrate this thing to energy. So bear with me and give it about a minute. All right, so we have been running for 600 seconds. So it's about 10 minutes. It took me a lot less time for this to look really, really nice. So let's figure out the spectrum and figure out what we're doing. Now, as you know, this over here on the left side is low energy, and over here on the right side is high energy. And we want to assign these peaks to energy so that we know how the energy progresses. Well, I actually know what all of these are, but even if I didn't know, I could pick out 2 of them without too much trouble. If you have a cesium-137 sample that you purchased from someplace like United Nuclear, then you know that there are 2 peaks that are generally associated with cesium-137. One of them is typically listed as 662,000 electron volts. That's 662 keV. The actual number is 661.66 plus or minus a little bit. But 662 is where most people tend to put it. And that's probably this big guy right here. In fact, I know for a fact it's this big guy. But I mean, if you didn't know anything about this, if you were just looking at it for the first time, you could probably deduce that since there's nothing over here, and you know that 662 is the highest peak that cesium-137 puts off, and this is a very pronounced photo peak, we can imagine that this is 662, and it is. So let's put our mouse right here, and we're going to hit B for begin, and then we're going to put our mouse over here where it ends, and we're going to hit E for end. And then we've highlighted this whole area as a region of interest. Now we might be confused about what these guys are, but I'll tell you in a minute what they are. That looks like a little bit of a peak too, and it is a peak, but what could it be from? I'll tell you in a second. This giant one over here, though, is really, really low in energy. And we know that the second most common peak that to be found in cesium-137 occurs at 32 kiloelectron volts. That's probably this guy here, right? Now, of course, it is. I already know that that's what it is. But if you didn't know any different, you might think and you might come to that suspicion. So this is why cesium-137 is a good isotope to use. for calibration, because it's really easy to figure out what everything is, even if you don't already know the calibration. So put our mouse here, we hit B for beginning, put it about here, we hit E for end. And you might say, well, how do I know to put it right there? I don't, but mathematically, being reasonably close on either side of this will work out pretty close. You'll find that expanding and contracting this ROI is not going to make much of a difference because of the way the math works to figure it out. Okay, so we have our 2 points, our 2 data points for calibration, we think, right? So let's go to data acquisition and analysis, which is part of the software. And let's see, we're not showing energy calibration yet. Okay, so we'll show that in a second. Let's go up to the main window. This is the main little window. And we're going to go to energy calibration. Let's clear the window here and go back to energy calibration. And how do we energy calibrate? Well, we hold our mouse over the ROI in question. This is the highest energy one right here. And we just fill in the information. Okay, first we need to know what's the mean. The mean is, in arbitrary units, is 46.885, plus or minus. 46.885. All right. And what's the standard deviation from the norm? It should be 1.95 is about right. 1.95. It's changing. Oops. It's changing a little bit, but it's pretty close to 1.95, right? It goes up, it goes down, it goes up, it goes down. And the energy, we're going to stick with 662. It's actually 661.66, but that's pretty close. Now let's go over here and look at this guy and see what it says. All right, its mean, now that I put my mouse on it, its mean is 2.93-ish. We'll say 2.93, close enough. And its standard deviation is 0.379. 0.379. And its energy is about 32 keV. And I'll explain a few things in a minute. We're going to fit linear. It's actually better to fit sloped and have more information and everything, but for right now we're going to fit linear. That means we're going to draw a line of change in energy with respect to channel, if you like. That's how that's going to work. And the energy unit is in kiloelectron volts. That's thousands of electron volts. Don't worry about right channel unless your unit uses right channel. My unit's only using left channel, so we're good on audio. So click OK. And we're applied, if you like. So let's go over here and say use energy calibration. Boing. And now we're fully calibrated down here with energies. You see all the energies? I should point out something. Do not set your calibration using energy units. See, if I put my mouse over here, it shows all my standard deviations and means and for the ROI, but you notice they're all in kiloelectron volts. So if I were to go down here and try to enter those into the calibration, if I entered those into the calibration, everything would go nuts because they would all be wrong. You see what I mean? You need to, if we wanted to recalibrate this, we'd want to go and uncheck this box first. So let's quickly figure out what the rest of this stuff is. All right, what is this right here? Well, according to the mouse, let's begin and we will end. According to the mouse here, in this region of interest is around 84 kiloelectron volts, and that's not far off of reality. I know that this one is actually between 75 and 80. It's actually 2 peaks put together, but you can't tell because they're too close to one another. Now, these come from X-ray fluorescence. Basically, high-energy betas and such are actually hitting, high-energy gammas and so on are hitting the actual lead that surrounds the detector, and they're causing characteristic fluorescence, just like a black light hitting a white object, you know how it reflects back at you. But fluorescence in the X-ray spectrum, so way high up in there in the X-ray spectrum, if I can say it correctly. And since X-rays come from changes in electrons and electromagnetic changes, then we know that this must be coming from X-ray fluorescence from the electrons around the atom's shells, if you like, around the nucleus. Whereas a gamma ray, like this guy over here, being a gamma ray, must come from the strong nuclear force that's coming from something called an isomeric transition. Basically, put the nucleons, the protons and neutrons, are relaxing and coming together and releasing surplus energy, is a kind of a simple way to put it. Now, what are these two guys here? This is called a backscatter peak, which we're not going to highlight it. These are basically photons that were actually reflected almost completely backwards, like they bounced right off of the crystal and they scattered. Backscatter. You know, like in the airport, they have the backscatter X-ray machine that they tell you is safe even though it's not. Well, this right here would be the same sort of thing. This is backscatter. This right here is called a Compton Peak. It's kind of the opposite. It's photons that have kind of reflected off of the crystal at an angle, but they're not really reflecting backwards. They're just at a slight angle. And then you have this whole entire continuum, this Compton continuum here. This is called the Compton plateau of various scattered photons ranging in their angle of scatter because they get bounced off of the crystal. They don't all perfectly get absorbed. And then you have the Compton Peak, you have the Compton Plateau, you have the backscatter peak, the X-ray fluorescence. These guys down here are actually created by X-rays after the atom relaxes, because you see cesium-137, as I said, it decays into barium-137M, and then barium-137M decays into barium-137, and you have both electrons that are here, which are releasing energy to calm down, and then you have the primary nucleus, which is releasing energy to calm down, and everything else here is just gravy. So there's cesium-137, one of the neater isotopes out there. It's an incredibly useful isotope to have in the lab. I could not live without cesium-137. Use it all of the time. You can also look for cesium-137 in your local soil. It's been there since nuclear testing back in the 50s and 60s. It could be found there. It can be found after Chernobyl, after 3 Mile Island. In fact, if I have soil samples from near 3 Mile Island that show trace cesium-137. It can be found from Fukushima. I shouldn't laugh, of course. That's as I was laughing about the academic aspect of it, but as I think about it, cesium-137 has also been responsible for a huge toll in humanity. I don't want to actually claim how many people have been affected by it, because I would have to actually sit down and research a whole bunch of peer-reviewed documents to know what that actually is. You know, be it tens, hundreds, thousands, millions, zillions, trillions, infinity, etc. So I'm just going to say that it is a known fact that cesium-137 has contaminated significant portions of the Earth and is responsible for troubles. We'll just put it like that. That way the pro-nuclear folks won't jump on me and say that I'm demonizing it, and the anti-nuclear folks won't jump on me and saying that I'm trying to hide the issue, because I usually get attacked by both sides at the same time, which I always get a kick out of. But there you go. And this has been Tom from anti-proton.com, and there you go.